Oh, sorry, I just realized I was muted. I was muted, but I'm glad it looks okay. Okay, cool. Okay, I'll give it until like 3 after. You guys joined early today. You're excited to learn about trees. Fair enough.
I have a
You were the
question.
catalyst, Jonathan. Okay, so if you guys can still hear me, that's great. Before we get started, I just want to know what people's experiences are with trees. I know last time we did a little bit of work with trees, but I want to make sure that, if we have new people, that they understand what a binary search tree is in particular. And feel free to shout out your answer or type it as well. Either works. Okay, so first time for someone. Awesome. Hey, cool. Okay, I'll assume it's everyone's first time then. Just waiting on a couple of other people typing as well. Okay, someone knows their tree traversals, but having issues applying them to problems. Okay, I don't know if this was the same person, but we had someone say that last time as well. Today we're still going to go over some of the basic tree traversals. So just to give you a heads up if you don't want to, watch that session, but in the future, I'm planning on doing a Q&A to figure out what problems people are having issues with, specifically like leak code problems. And I think I have gotten a lot of people saying like, oh, I want to know how to do specifically like true problems, not just traversals. So we can definitely do that next time. I don't think we're ready for that in this session because I think most people are still learning what trees are. So it looks like someone said they weren't in the last session. They joined a few days ago, but they have a little bit of experience on trees. Okay, perfect. So we can just do a quick recap, and then we can go into, I'll show you guys how we built a tree last time. And then we're also going to go and figure out how to find a specific node in a tree, and then we'll learn more about depth first search, and then I'll briefly tell you guys about breadth first search as well. Okay, cool. And Morningstar is going to help me out. If you guys have questions while I'm doing the session, I can't really see the chat, so he'll just, let me know if anyone's typing in the chat. Otherwise, I really like it when people shout out questions. I'll pause and ask for questions as well. So feel free, I want this to be a very engaging conversation rather than like a lecture. So feel free to ask any questions that you need. Okay. So we're going to go ahead and share. And then Jonathan, feel free to start recording whenever. And let me know whenever you start. Okay, awesome. So I'm going to go ahead and click draw what we had last time just to give a recap on what a binary search tree is. So these are nodes. And a binary search tree is just another data structure that stores data. That's basically it. So if you guys have heard of like arrays and array lists, that's usually a way of storing data, right? So this is an array, and we usually have different indexes that denote different parts of the array. But here with a binary search tree, it's structured a little bit differently. So we typically have the first node, which is called the head. Put an 8 here. And then usually it has 2 children. So it kind of looks like an ancestry tree. So we have a left child and a right child. And then if we look at the subtree, so this is called a subtree. This is the head of the subtree, and it has a left child and a right child. Does that make sense so far?
I don't know if it's just me, but it seems like you were streaming your Discord.
Oh, can you say that again?
You stream in Discord, not the notes that you want to share.
Oh, you can't see it?
No, I can't see it.
Thank you for letting me know. Okay, let's see. So screens, entire screen. Okay, can you see it now?
Yes.
Oh my gosh, thank you. I'm glad you said something. What'd you say? It is a little bit hard to hear you. Okay, so I'll just explain again. So this is basically our head, and then our head will have a left node and a right node, and those are called children. So we have our left child, and then we have our right child. And then this, I was saying, is like a subtree. So we have a head in our subtree, and that also has a left child and a right child. And sometimes it can have like one child on the left, and then it points to null here. Sometimes this last node can have no children, so we can have different combinations. But the biggest thing about a binary search tree is its searchability, right? So we can find things a lot faster than we can find in an array. In an array, we usually check the first value, and then the second value, and then the third value. So we have to go through sometimes the entire array to find our value. But here what we do is we check the first node, and let's say our first node, it has a value of 8. Say 11. Usually we start at the head, and if that number is greater than this value, we go to the right. If it's less than this value, we go to the left. So we're splitting our chances of finding something in half every single time. So that's more of a logarithmic function, which is a lot faster than a linear function. And a linear function is used for array searches. So here, for example, we might have our 11, and we'll have a 9 here, and then maybe a 5 here, and a 6, right? Because we have an 8, and let's say we have a 5 that we want to insert. The 5 will go to the left of the 8, because it's less than an 8. The 6, it's still less than the 8, so we'll go to the left, but it's greater than the 5, so we'll go to the right of the 5 for the 6. Does that make sense? I don't want to talk too much about this since we did this last time. I just want to make sure people kind of could recap and understand what a binary search is.
Yeah.
Okay. And if it doesn't make sense, let me know. I can spend more time on it. I know. Okay. Awesome. So last time, this is still the recap. Last time what we talked about was building a tree, right? So we have a class called tree node. And the class, so the node itself has a value, right? So if we go back here, you see that it has a value, number 8. But then it also has a reference in memory to a left tree node and a reference in memory to a right tree node. And we've also built a constructor here. So you don't have to worry too much about this, but this is what our tree node class looks like. It has just these 3 values. Now, last time what we did is we had an array of numbers, and we used our insert node recursive function to build a tree. So again, we won't talk much about that because we did that last time. What I do want to talk about is how to find a node. So let's go back to the whiteboard, and I'm going to clear. Okay, so I'm going to create a actual binary search tree, and we're going to go through a exercise. Okay. These values. Okay. So let's say we want to find the number 9, right? So we start here at our 10. So what do we do first in order to find out if the 9 exists in the tree?
Check the value of the head. If it is the 9,
I think someone may have to repeat what you said because it's really hard to hear you.
we need to check the head value first.
Okay, check the head value. Okay, so we've checked the head. So our head is 8 and our value is 9. So what do we do after that?
So now we need to compare it if it is greater than or less than. Like it is the binary search tree. So we need
Okay.
to go after that.
Yep, exactly. So 9 is greater than 8. So we found out 9 is greater than 8. So where do we go next?
So we need to go right side of the head.
Yep, perfect. Because our 9 is greater than 8. Then what do we do after that?
Then we repeat the process again. Like check the head element. If it is like equal to a 9, then we count it. Otherwise we check if it's less than. In this case, it is less than. So we go to left side of the head node.
Yeah, exactly. So, and I liked what you said before. You said we repeat the process, right? So recursive functions are typically a repetitive process. So he's saying we check the head and we see that our value is greater than the head. So we go to the right. Because remember, the right children are always greater, the left children are always smaller. So we go to the right. Now the 10 is actually bigger than the 9. So that means we have to go left because 9 is less than 10. And now you can see we compare these two and they're equal. So we can return true. So this will be like a true or false function. Either the node exists in this binary search tree or it doesn't exist. Does that make sense to everyone?
Yeah, exactly. It does. It does really make sense.
It makes sense.
Yeah, sure. It does.
Awesome. Okay. All right, so we're going to go ahead and code this. So remember, we've already built our tree. So our tree is called tree node head, and we gave it a value of 8, and its children were null and null. But then what we did was we used this array to build our tree. So here you can see we've inserted a node and created a new tree node for every single number, and then we've added it into our tree. So now we have our tree. I'm going to write a comment here to find a node. So we're going to first create the function. So I have a couple of functions that have been defined here, but first what we're going to do is create our find node function. So let's walk through that. And our parameters are the value that we want to find, and then the actual tree that we're finding the value in. So based off of what we did just now, can anyone kind of shout out the answer as to how we'll start coding this? And if no one knows, that's okay. We'll walk through it together.
Firstly, we have to check the head first. We have to compare the head and the value actually. And the actual value we are searching for.
Mhm. Okay, so let's say if value equals head dot value, then what do we do?
Yes, then we return the value, of course. We return maybe now we have found the value, right? Because we are just using the object or the node, right? So if the value is equal to the head dot value, that means that is the value we are looking for. Then we return the value. We
Yep,
return the head,
exactly.
something like that.
So we can, in this case, we can just return true or false.
Yeah,
But yeah, if you
it's a
function
boolean.
with, yeah, but if you want to make a function with int, yes, we can just return the value itself. For now, we'll
Yes,
do
yes.
an easy one. Like you said, just we'll check first if the value is equal to head of the value, we return true. And that's actually one of our base cases. Okay, so let's say the value is not equal to the head. So let's say we're here again and we checked is 9 equal to 8. No, that's not true. So what do we do?
So the next thing we compare is the value greater than the head dot value or less than the head dot value.
So it's value greater than head dot value. And I'll just do this, or I'll do if value is
Value.
less than
Like
head
we can
dot.
use else statement here.
We can, but because we're returning something, we'll never reach that if statement anyways.
Like we can return in if or else statement. Like we can return the
Sorry,
next
I didn't get what you said. You said we return something. What will happen?
like if we
So
return
sorry, I
we
couldn't
can
hear the
put
other
return
person.
statement inside the if statement, calling the other function.
Yep, exactly. But is there something we may have to do first? So let's say, for example, we are down here. And let's say, let's say this is an 8. Let's pretend, that these are different values. And we're already at the bottom of the tree. So now 9 is less than 11. And we want to go to the left node. But is there a left node here?
Oh, it is null.
Yeah, so this is not. So do we have to do anything else other than just calling find node again?
No, we have to check exactly. Exactly, we have to check if the Let me think. uh, Before you go to the left, because now it's less than, right? The value is less than the head to the value. That means, okay, since it is less than, then definitely what we are looking for might likely be on the value is less than. So which means, yeah, I'm kind of confused here.
No worries. Okay, let's go through this one. So you guys are
I
really close.
think if the value is greater than a header's value, then we go right. But we need to first check whether the right one has a node there. If it's none, then we return false because we cannot find it, right?
Exactly. Yep,
Yeah.
exactly. So I'm just going to repeat what you said. So if we're here, right, and our left and right children are null, or even one of our children are null, and so our 9 is less than, or sorry, our 9 is greater than an 8, right? So I put an 8 here. We want to go to the right, but there's no node at the right, right? It's null. So we want to check first, is it null? If it is, we've reached the bottom of our binary search tree, which means we haven't found the node. So we
So that
want
will
to check
mean
here.
that will mean we'll insert it there. Oh, we are finding. So we are finding it return false. Exactly. Yeah, I will get it. So if the value we are looking for example, in this case, we said that we are going to the right, right? Because the value is greater than the head dot value, right?
Yep,
So we go to the right. But if the right is null, that simply means the value is not in the tree.
right. Exactly. Exactly.
Okay, okay, I get it. I get it now. I get it now.
So we can say if head dot, because again, value is greater than head dot value, we want to check the right. So if head dot right is not equal to, then we do something, right? Else we do something else. And then we can do the same thing here, but with head dot left. Does that make
Yes.
sense? Mark?
Yes. Yes. Yes.
Yeah,
Yes.
it totally makes sense.
Okay, perfect. So if head dot right is not equal to null, what do we do?
We compare the
Like
value
we put a return
and
statement
the
calling the other
left
function.
and the right, right? We compare the value and the head dot right value,
So
right?
we're Close, very close. Also, I heard someone else say something, but I couldn't quite hear that. I want to
We
listen to
can
everyone's answers before I say.
Yeah.
return find node value same and head dot right.
Yes, exactly. So what the first person said, sorry, I don't really know names, but the first person said that we're going to check the right value and the left value. So we already did that here, right? So we're checking, is it greater than or is it less than? But then once we determine like, okay, yes, our value is greater than our head dot value, that's when we go into the if statement. Then we're checking if our head dot right is not equal to null, we want to continue traversing the tree. So we're going to actually we're going to return find node, and then we're going to pass in the same value. But then what will we pass in here?
Head
Right.
dot right.
Yep, head dot right, exactly.
Yeah.
So we can do it again, same thing, right? With the mirror image, but we'll do head dot left. Now, what do we do else? So if our head dot right is null,
Return
what do we do?
false.
Return false.
Exactly. And then these are all if statements, right? So if we never go into these if statements, we have to have a return at the end. And what would we return?
I guess it should be return false.
Okay, should we try it out? See if it works.
Yeah.
So find node. So we'll call, say, Boolean exists equals find node, and then we'll have our value and then our head. And I'm just going to print it out. I'll just print out exists. Okay, so this is our head, or this is our tree. Remember, the tree has these values plus the 8. So what value do you want to check exists?
14.
We can try 9.
If you're not answering the question, can you please mute yourself? I think someone might not be muted. Okay, so someone said 14. Did someone say 14?
Yeah, anybody basically.
Okay, so what are we gonna get? Sorry, one sec. I'm gonna mute. I think it's a little loud on someone's end. I'm not sure who.
Sorry.
Sorry, I just muted someone because it was a little loud on your end. I can unmute you in a bit. Okay, so 14. So are we gonna get a true or a false?
True. We're
It'll
gonna
be a
get
true.
a true.
Return true.
Yep, true, because we have a 14. So let's run that. Okay, it looks like we got an error. So find node doesn't exist. That's because we haven't used BT. There we go. Okay, so we got a true. Awesome. So should we try another number that's not in the tree? Feel free to shout out any number.
We can try 0.
0. Okay, let's try that. False. Perfect. So it looks like we have successfully created a find node function. Does that make sense, you guys?
Yes.
Okay, perfect. So when we traverse trees, there's a lot of different functions that are pretty common to tree traversal. So we have something called a breadth first search, and we have something called a depth first search. So like going back to this whiteboard, a depth first search means you typically go all the way down until you hit a child that has no children. So a child that has no nodes as its left and right child. A breadth first search is where you search using level. This is one level, this is a second level, and this is a third level. It's kind of like searching by generation. Does that kind of make sense?
Yes.
Okay, and we'll go through examples. So we won't probably have enough time to do both depth first searches and breadth first, but we'll kind of focus on depth first. So depth first search, again, is we want to like try to go all the way to the bottom to then, return a child and then return another child and then return the next level. So we're basically returning a bunch of the children that don't have children first. And I'll show you what that means. So we have something called, and actually, let me draw this again. So we'll do like a 10. Six. Technically, we can have something like this, right? 2, and then 13. We can even have something like that. So this is still a binary search tree. It's just not balanced, right? So these are pointing to null. This is null. And then these are. So we have something for depth first search. It's called DFS. You guys have heard of that? Where we have different ways of traversing. So we have something called an in-order traversing. Just gonna write that down. Hopefully you guys can read my really bad handwriting. So an in-order traversal, we basically print all of these elements in. So what we do first is we check the left child first. Then we print out a node, and then we check the right child next. So with an in-order traversal, all of these will be printed in order, right? So it'll be 2, 3, 6, 7, 8, and then 9, 10, 11, 12, 13. So what happens is we first check, is there a left child? Yes, there is. And again, we check, is there a left child? Yep. Is there a left child? Yep. Okay. So then we check again, is there a left child? No, there isn't. So the next thing we do is we print the value of the code. So then we print a 2. Then we return, we go back up the call stack, right? Because these are all function calls that are stored on the stack. So we go back up and we see a 3. And so we return this value, right? Because we've already checked the left child. So we return that value, 3. Now, is there a right child? Nope, there isn't a right child. So next we go back up the call stack and we return this value because we've already checked the left child right here. So we get a 6. And then we check, is there a right child? Yes, there is a right child. But then we check, is there a left child with this right child? No. So then we pop back up the call stack and we get a 7. Then we check, is there a right child? Nope, there isn't a right child. So then we pop back up the stack here. We've already printed this value out. We've already checked the left and right children. So then we pop back up the stack here, and then we print this value, right? So it's the next value. So 8. And we've already checked the left children here. We've already printed out the value. So then we check the right child. We check the right child, which is the 10. And then again, the function, it's recursive. So we have to do all these different calls again. So we check the left child. Does it have a left? Yes. Does this one have a left? No. So back up the call stack. And we print. Does that make sense so far? It's kind of confusing if you haven't done it before, but hopefully this kind of makes sense.
I
Yes.
have a question.
Yeah.
Like
Definitely, it doesn't.
multiple times on one node. Like if one node has left child or node has right child, so it is returning its value only.
Yes. So right now I'm just showing you if we're like printing the values out. Returning values is a different thing. So what I'm showing is in a binary search tree, things are actually ordered, right? Ordered by less than or greater than. So what an in-order traversal does is it's printing out all of the values in order from like the smallest amount to the biggest amount. So it won't necessarily return the node, but it's like printing out. And the way that we do the in-order traversal is we check all the smallest children first. And once we get to the smallest child, which is right here, then we print that out. And then we go back up to the second smallest child, which was the parent of this one, right? And then we print that first before we go to the right child, because the head is always going to be smaller than the right child. Does that make sense? That's why we check left first, because it'll always be smaller on the left. If there's nothing on the left, we print the node itself, because that'll be the smallest node. Then we go to the right to get the second smallest node. Does that kind of make sense?
Like first we are going on the left side,
Mhm.
then we are going the right side. So what does the 3 going to print more than one times? Like on the 6 node 6, we go left side first, then come
Oh,
6.
it won't print more than once, because what's happening is, so let's say we have our, like, let's say we're here, we're at our 3, right? So we're at our 3, and now the first thing we do is we check left, right? So we check left, but what happens is we store this function call on the stack. So then we check left, and our left is 2. And 2, we start over. So we check left. It doesn't exist. So the next thing we do is we print. Perfect. Then the next thing we do is we do the right. There is no right. Perfect. So what happens is we finish this entire function call for 2. Then we pop this off of the stack, which was function call 3. But with function call 3, we already did this. So it immediately returns the answer for 2 in this function call. And then we immediately chronologically go to the next order of operations in the function, which is printing out this node. So it'll only print each node once, if that answers your question. It won't
Yeah.
check this part again, because we've already returned the results of 2 into this. And then we, like, just like a normal function, right? So the easiest way to actually think about this with recursion is, let's say we have actually, let me type this out here. Actually, sorry. Make it easier. I just have a new. So I'm just going to create a random function. Say function 1. And we'll say it has int param. So let's say we call, function. Sorry, we return function 2, and then we have a value equals function 2. Int fun2 equals function 2. This is just going to be pseudocode. And then what we end up doing is, maybe we call function 3 now. Equals function. Then we have another one, function 4. And then let's say we've defined our other functions, right? We have function 2, 3, 4. And these functions do something. We won't say what they do, but they just do something. So let's say we have function 1. So we have our int parameter. Let's say we pass in param here. So we have our function 2, and that is set equal to function 2. So we call function 2, right? So we come here. Now let's say function 2 calls function 4. Equals function 4. So then function 2 calls function 4, and we do something. Let's say we print something here, right? So now that we've printed something, we're finished with this function, but we go back up to the call stack, which is function 2 calling function 4. And that's it. We don't have anything after this. So then we go back up to the call stack here. And this is where whatever gets returned here is set equal to function 2. But we don't execute this function again. We go to the next function. So it's the same thing with recursion. If we call ourselves over and over and over, right, we call function 1 over and over and over until we get to the end of the call stack for function 1. Then we've already set our value equal. We have a variable function 1, but then we move on to the next function call. we don't execute this again, if that makes sense.
Yeah, I got it.
Okay, awesome. So any questions about, I know I erased all of this, but any questions about in order traversal?
No.
Okay, awesome. Let's go ahead and code it then. So we have our in order traversal. What do you think we do first? Remember, we want to check left, we want to print, then we want to check right.
You could do if head dot left is not equal to null.
So we wouldn't have to use this necessarily. We can just use head, right? So we can check. Oh, did you say if? Sorry, I thought you said this. So if head, you said is not equal to null.
Head dot value or head dot
We can just return, right?
Uh-huh.
And then what? So that's our base case. If head is not equal to null, we'll just return. But what if it
should be
is?
equal to.
Oh, equal to. You're right. My bad. So if head is equal to null, then we return, right? The head is null. There's nothing really to do. But if it's not equal to null, how do we do our in order traversal?
Like first
If
we
head
print
dot
our
left
value.
is not equal to null, you'd probably do a recursive call for in order.
Okay. So in order.
And you would the parameter you would put would probably be head dot left.
Okay.
They will do the same thing for the right. No. Yeah, we'll do the same thing for the. After we get this,
And then what do I do next? So we've checked if our head is head dot left is not equal to null. So then we call in order head dot left. So we pass in our head again and we start all over, but with head dot left. So head dot left equal to null, return. Is head dot left basically not equal to null, then we call in order. But what do we do after we check all the left values? Do you guys remember?
We need to print our value.
Print our value. Dot value. Okay, what do we do next?
Go on the right side.
Okay, should we try that? See if it works.
It will work.
Would you have to print after that head dot right as well?
No, so the way that we do it is we check left first.
Okay.
And then once we get all the way down to null, that's when we print out the value. If we then pop up back to the calls, like the call stack will have those function calls stored, then we'll pop back up to the node. And remember, we're already past this point and we're past this point. So we're just going to the right. So if we call head dot right, or sorry, in order head dot right, it'll start all the way over here and it'll check the right node's left. Once it's exhausted checking that node's left, it'll print out. So it'll always print out after checking the left values first. And we can go through the diagram again after this to just, make sure that we understand that part.
Okay.
So let's go ahead and try to print. So in order reversal. And I think we were going to get an error, actually, so I'm going to show you guys why. So in order. Order passing head. Oh, it looks like we did get an error. Let's see why. Oh, because we did head equals equals. Okay, perfect. Okay, perfect. So do you see where we printed out all of the values in order?
Yeah.
So does that kind of make sense?
can you go back to the in order function?
So let's look at pre-order now. So pre-order, once you know one of these, it's really easy to at least code the rest of them. So I'll just show you.
Can you go back to the in order function?
So we have our 8 again. We're always going to start with 8 because that's a nice number to start with, honestly.
Someone asking to see the function again.
Oh, to show the function again? Sure.
Okay, what's the question, bro?
So actually, I was going to say I think we can do this because we're already checking.
We can remove the if statement also.
Yeah, we can check. We can remove. Exactly. We can remove this. So it's really simple, actually. It's like probably the most simple recursive function. So if we run that, we didn't put a space here, but that's a 1011. So the reason for that is we don't have to check if head dot left or right are null, because if they are null, we go into this value with head equaling null, and then we check already, is head equal to null, then return. So we then go back up the call function, or the stack. So it's literally, if head is equal to null, return. We just call it in order, head dot left, we print, and call in order, head dot right. Simple as that. And then, sorry, can you read the question? You were saying someone asked a question.
No, he was asking just to show him the function.
Okay.
Yeah, that's all. I'm okay. That's what I want. That's
Yeah,
all.
and I'll send this code. I sent last week's code as well in the chat. Or sorry, in the announcements channel. I think I sent it as a thread. So with pre-order, hopefully that was enough time for you to look at it. And again, I'll send it. So you should have it handy then. So we'll say this. And 3. Okay. So if in order was we check left first, print, then we check right. What do you guys think pre-order is?
We need to print first.
Print.
Okay, print, and then
Left
Then left.
and then right.
yep, exactly. And then while we're at it, what do you think post order is?
Print at last.
I mean, it's like,
Yep, so left, right, print.
I guess I haven't used it.
Do you guys want to go through the example, or do you want to just try to code it right away?
Like we can code it. It is
Okay,
simple.
let's. Yeah. So pre-order. Let's do pre-order.
You could just copy and paste it and then readjust the lines.
Sure. Yeah. Let's do that.
Holy shit, serious.
So where would the print go?
Like after checking the null value.
Okay. And where would the print? Where would the print go in this one? In the post order.
At the end.
Perfect.
So after
Okay,
the
so
right.
let's try those.
We need to change their name first.
So I think, oh yeah, you're right. Actually, you're right. So we have in order here. So we're going to want to use pre-order. Good call. Pre-order. So just not to have any confusion, let's do pre-order first. Because if we have all these values printed out, it might not make sense. Pre-order, and then we have our head. I was looking at the output. I was like, 12, that doesn't make sense, but it's 1 and then 2 and then 3. So it looks like those were not, there wasn't very good spacing right there. Okay, so pre-order, let's run that. So now we have basically what the tree looks like, right? So we have our 8, and then we have our left child and our right child. So 8, 7, 6, and then the left children and right children of this one, and then this is the left children and right children of the next one. So this is pre-order. So we're printing the value first as we go down, and then we call left every time. So what'll happen is we print this first, then we go left, and then we print it, then we go left. So print it, then we go left, which we can't do, so we go back up. We've already printed and gone left, so we go right. So this one should be like 8,
Also, I should
5, 3, 7. And then we go right and we print it, 10. And then we go left, and we print it.
Yeah.
And then we do 12. Does that make sense? So we print before we go left. We still go left first every time.
Good.
And then the other one is we go left and then right, and then we print it. And then so basically what ends up happening is for post order, we end up here. And then all the values that are printed are just based off of the function call being popped off of the stack. So first we'll print this because we get to the very end of the entire string. Then we pop it off the stack and go back here. And then we print that value. And then we go left and print that value. So let's try. So this won't really have any rhyme or reason, but the other one will be the opposite, right, of our in order. So let's try post. You can see that post.
Yeah, it is. They're
Okay, so this time it looks like it's a little bit off. So let's look at what's going on there. Post order,
If you want,
head down left, head down right. We have 1, 3, 2, 4, 5, 6, 7.
you can
Let's see.
like
Oh, you know what? This might be
people
right because we've inserted these in a weird way. You may have to draw it out. So post order, if head is not equal, if head equals null, we return. Otherwise, we put our left in and then our right in, and then we print the value. So that should be right.
8 is right. Like we can see 8 at the last.
Yeah, so 8 is our middle. And I think that's the same here. So I believe it actually should be the opposite of our pre-order. Let me print out our pre-order to make sure. So you'll always want to verify just in case. So let's do a system data line, and then we can show the difference. Okay, so we have our 8. So the first one is going to be our pre-order, which makes sense. 8, 7, 6, 5, 4, 2, 1. Because our middle will be printed first, right? Before we keep going down the stack. And then this one is 1.
if I say you do this,
Which actually, yes, this does make sense. Because 1 is going to be our bottom child, right? It's not going to have any left or right children. So I think this one is right as well. Okay, perfect. So do you guys understand the difference between traversing in order, pre-order, and post-order? Okay, awesome. So I'll briefly, we only have 12 minutes left. So I'll give you a brief overview of what level order traversal is. It's up to you guys. If you want, we can go over how to implement this next time. Otherwise, we can kind of move on to a new topic because I know this is already our second lecture on trees. So with level order, we're actually going to be going through each level for each order. So with DFS, depth first, go down all the way down to the left or all the way down to the right, and then we print nodes by going down the depth of the tree. The breadth is by level. So we'll first grab this first value, and then we'll add our children to a queue. Then we grab whatever child was first in the queue, which will be this child, number 2. We add its children to the queue. And then we grab the next value in the queue, which is actually 3, right? Because we put 1 in there, we put both children in there. So let me draw this again.
Okay, talk to you later.
I should probably figure out a way to just keep that 3 there and not have to redraw it every time. So 8, 6, Okay. So we have our 8, and we take its 2 children, right? So this is one level. And we add it to our queue. So we add a 6, and we add a 10. Then we recursively call whatever's in the queue first. So our 6. So then this is our subtree, and we take its children, right? So 5 and 7. And we add it to our queue. And we've already visited this node. Right? So we do whatever we need to do, and then we check recursively what's the next node in our queue. So we then check that value. So that value's children are 9 and 11. So then we add 9 and 11. And then we check whatever's left of the queue, and it's 5. So after we've already traversed this level, and usually we add a null here. So a null to make sure that this level is finished. So that's a level. This is a level. Then we usually insert a null when we get to the end of all the children. And then here's another level. And this is helpful when we're doing non-binary search trees. So let's say we have an 8, and it has like 4 children, right? And we can add all of those to the queue and then add a null at the end. So then we pop whatever's in this queue, grab it, to 5, we take its children, it doesn't have any children. We're done with that one. Then we grab the next value of this level, and that doesn't have any children, and then grab the next one and the next one. So actually, sorry, this is an entire group. This is an entire level, right? Even though it has different parents, it's the same generation. So we'll actually put a null afterwards. Does that make sense? So for the reason or the way that we figure out where to put the null is the first one, we put the 2 kids, right? And then we put a null as soon as we put all of its children. And then as we're going through these 2 values, as soon as we see a null again, we've already added these 4 values, that's when we put another null. So every time we see a null as we're traversing through the queue, that's when we add another null to the queue, because that means we've gone through all the children in that generation. It's easier to see when you have like more levels, I would say. But this is something that we can do next time as well. Does that kind of make sense though? Like the concept?
Like we need to maintain other data structure like queue as well.
Yes, we need to use another, and we pass it in, yeah, as a parameter in the recursive call, or we can have a global variable. So it isn't always recommended, but you could do something like that. Cool. So I'm going to open it up to questions. We have about 8 minutes left. Let me know if you have any questions. I'm going to unmute the question. Okay, cool. No questions. If you guys want the code, I'll post it probably in the announcements or general channel at some point today. And then at some point today, we're also going to put out a survey. So please make sure to answer the questions in that survey. It really helps us figure out what sessions to do for you guys, because we only want to do sessions that you're interested in. We don't want to do like random sessions that people don't want to watch. So yeah, just let us know in the survey. We'll send out the code too. And I'd love to get feedback. If you guys learned something, that's good. Or if you just, stuck around to recap whatever you already know, that's good too.
Hey, thank you.
Yeah, no worries. Thanks, guys.
It's really our pleasure for everything. Thank you very much.
Yeah, thank you.